Welcome back. Today we're going to do our first new lesson. So we're going to talk about isotopes. I'm going to be switching back and forth between this screen and a screen that I can write on, but you should have a copy of this PDF note no matter what. So today when we talk about isotopes, I want to pose a question to you first, and it's something that you might not have thought of in grade 9 or 10 chemistry, but some of you might have. So if you think about the periodic table, and it would be really handy if you had a copy of your periodic table in front of you. So if you don't have it, go ahead, pause the video, grab your periodic table, and come back. If you take a look at the masses on the periodic table, you're going to see that the masses on the periodic table actually are not even. They're decimals. In grade 9 and 10, I was giving you rounded masses, but if you take a look at the atomic mass of each element, it's usually got 2 or 3 decimal points, depending on the periodic table that you have. So the question is, if we know a proton weighs 1 and a neutron weighs 1, where are the decimals coming from? So this is actually something that can be answered to us through isotopes. So let's do a couple definitions first before we get to the math. So two atoms are isotopes if they have the same number of protons, but they have a different number of neutrons. So essentially an isotope is the same number of protons. The number of protons actually can't change. The number of protons defines what an element is. So for example, lithium is lithium because it's got 3 protons. So we can't change the number of protons, but you are able to change the number of neutrons without impacting the identity of the element. What this will change, though, is its mass. So let's review that really quickly. This means that isotopes are atoms of the same element, so they're absolutely the same element, but they do have different atomic masses because they vary in their number of neutrons. Isotopes have a different number of neutrons that exist in their nuclei. So let's talk a little bit about what we call isotope notation, how we actually represent different isotopes, right? Because we've never had to list different versions of the same element before. So with isotope notation, we're going to use a couple of different letters. We're going to use Z to represent the atomic number. So we're going to be using the atomic number. Remember, the atomic number is the number of protons that are in an element, and that's what an element is. It's defined by its number of protons. So we're going to first list the number of protons in that element. We're also then going to use A to represent the mass number. Just a reminder that the mass number is the sum of the number of protons and the number of neutrons. So for example, let's go down here first. To list something as in isotope notation, you would actually list it like this, where you'd have a nice big version of the chemical symbol. You have the mass number on the top here, and you have the atomic number in the bottom here. This is actually called standard atomic notation, and those of you that had me in grade 9, we actually started learning this in grade 9. So this is the exact same standard atomic notation that you learned in grade 9, just we're calling it isotope notation now. What's really nice about listing it this way is it makes it very easy for us to calculate the number of neutrons. Remember, the number of neutrons is going to be the difference between the mass and the number of protons. So to figure out the number of neutrons, I would want to take A and subtract Z. So the way that we set it up here in isotope notation, it looks exactly like the math is set up for you. So you would take this number, you would subtract this number, and that's going to give you the number of neutrons in that isotope. Let's take a look at a couple examples using magnesium. I'm actually going to switch to my other screen. There we go. Let's scroll. And while I'm here, I'm going to go ahead. I'm actually going to turn my camera off because I'm going to write on this. Actually, you know what? I don't have to write on this yet. We can keep the camera on for now. When I do the other math, we're going to have to turn that off. So we're going to take a look at the 3 different isotopes that are surrounding magnesium. So we have 3 different isotopes here. How do we know they're 3 different isotopes? We'll take a look. These numbers are different, right? They look slightly different, so they're isotopes of each other. We know they're all magnesium because they each have 12 protons. So the number at the bottom represents the number of protons. So this is magnesium. So every single one of them would have 12 protons. Just a reminder that in this case, we're not dealing with ions yet. So the number of protons is equal to the number of electrons. So as soon as you know the number of protons, you do in fact know the number of electrons. In this case, it's going to be the same. In this case, oh, we're thinking. Tighten this maybe. Where'd it go? Come back. There we go. Nope. Oh, it crashed. This is fun. Okay. I am just going to go ahead. I'm going to pause this just for a second, and I'm going to reload what I was writing on so I can keep doing it. All right. I am back. We are not crashed anymore. Hopefully we stay not crashed. So if we go back to the screen, you can see that the number of electrons is all the exact same. Now the last thing we want to do is we want to figure out the number of neutrons. Now remember, the number of neutrons is the top number minus the bottom number. So in this case, it'd be 24 minus 12. 24 minus 12 is going to be 12. For the next one, it'd be 25 minus 12, which is going to be 13. And for the next one, it would be 26 minus 12. That's going to be 14. So we can see that these are all indeed isotopes of each other. They have the exact same number of protons, but they have different numbers of neutrons. So they have the same number of protons, the same number of electrons, the same appearance, and the same chemical properties. So what gives it the appearance and the chemical properties is the number of protons and electrons and the type of bonding. The number of neutrons does not impact the chemical properties at all. The only differences between those isotopes is that they have different numbers of neutrons and they have different atomic masses. So let's talk a little bit about the role of the neutron. So if you had me in grade 9 or grade 10, I did mention this. If not, this is maybe new. That's okay. That's exciting. So let's talk about what the neutron actually does, because it doesn't sound very exciting, right? We're saying that the neutron can vary and that the neutron can vary and it's going to be the same element. We know it doesn't have a charge. So what does the neutron actually do? So in a small atom, you're going to notice that the number of neutrons and protons are often proportional. What that means is in a small atom, the number of protons often equals the number of neutrons. You'll probably remember this from your grade 9 Bohr-Rutherford quiz, right? When you're trying to memorize the number of neutrons, it was very often the same as the number of protons, or it was one off. However, as the atom grows, you're actually going to see the number of neutrons increase more rapidly. So what that means is if you pick a random element near the bottom of the periodic table and you figure out how many neutrons it has, it might actually have 10 or 20 extra neutrons compared to the number of protons. This is because large atoms have a bunch of positives that are packed really closely to each other, right? So bigger atoms have a bunch of protons packed really closely to each other in the atomic nucleus. If you remember grade 9 electricity, positives do not like to be close to each other. Like charges are actually going to repel. So we don't want the nucleus of our atom actually going and repelling itself, and that would make it unstable. So we need to put something in there that's going to cause those like charges to stick together. And the answer to this is the neutron. Remember that the neutron has a neutral charge. And remember that neutral objects are going to attract charged objects. So if we put a bunch of neutrons in here, the neutrons are actually going to attract the protons, and it's going to essentially be like the glue that's going to actually hold the protons and the neutrons together. So we say that the larger atoms have more neutrons, and we call it a stabilizing effect. So the larger atoms have more neutrons. That's a stabilizing effect, and it's helped to hold the atom together. So in grade 9, I think I actually used the word glue. It's a great word. So neutrons are actually the glue that hold the nucleus of the atom together. Let's talk a little bit about radioisotopes now, and the term radioisotopes. You might have heard of this before. Radioisotopes are isotopes that have unstable nuclei. So just because an isotope exists in nature doesn't mean it's necessarily stable. So sometimes the number of neutrons, if there's extra neutrons, isn't necessarily stable. So what radioisotopes will do is they'll actually decay. What decay means is it'll lose a neutron or two. Since it loses a neutron or two, it's going to decay to a more stable form. So a radioisotope might start with a certain number of neutrons, and over time it might lose some of those neutrons and decay to another isotope. We call that radioisotope. All right, so that's kind of the background information that you need to know about isotopes. Now let's talk a little bit about average atomic mass and why those decimal places come into play. So average atomic mass, in the periodic table, the atomic mass of an element is given in what we call atomic mass units, or U. So some of you asked me that in grade 9 or grade 10. I just said we deal with it in grade 11. So the actual unit for atomic mass is U, or sometimes it can be shortened to AMU. Essentially, it's just like the mass of one proton. So AMU is actually technically based on the mass of a carbon-12 atom. Why a carbon-12 atom? Because that's what we were studying at the time when we were looking at the units for average atomic mass. So the mass of a carbon-12 atom, an AMU, represents the mass of 1/12 of a carbon-12 atom. So in a carbon-12 atom, we know that there's 12 protons. So if we're looking at something that's 1/12 of 12, it's 1. So essentially an AMU, or U, is the mass of one proton. Since all masses technically are compared to carbon-12 then, we actually call it relative atomic mass. So when we say hydrogen has a mass of 1, that's actually relative to carbon-12. It's got a mass of 1/12 of carbon-12. Most atoms actually have more than one naturally occurring stable isotope. So most atoms that we're going to look at might have 2 or 3 or 4 different isotopes. That means 2 or 3 or 4 versions of itself, just with different numbers of neutrons. So the issue here is we've got 2 or 3 or 4 of the same element with different weights. So in order for us to figure out how much that element weighs, we actually determine the average atomic mass. So when you're looking at the mass on the periodic table, you're actually looking at the average atomic mass, the average of the number of isotopes that exist, right? So when you're looking at carbon-12, and if you look at carbon on the periodic table, it should say the mass of carbon is 12.01. Depending on how many decimals. That means that most carbons have a mass of 12, 6 protons, 6 neutrons, but there are some carbons that have a mass of 6 and then 7 neutrons, or 6 protons and 8 neutrons, and that's why you have that decimal, because it's an average atomic mass, it's an average of all the isotopes. So in order to figure out what that average atomic mass is, you need to know the different isotopes that there are, but you also need to know how many different versions there are. Maybe it's 99% carbon-12 and only 1% carbon-13 or 14. So we actually call that the isotopic abundance, or the percent abundance. That's going to tell you the percentage of the makeup in the environment. So it's going to help us to calculate that average atomic mass. So the isotopic abundance is actually fixed. So when you look at the isotopic abundance, it's fixed for every element in the universe, and it's actually got the same proportion. So it's an actual percentage of the population. Isotopic abundance is the amount of given isotope of an element that exists in nature. So I'm going to highlight that for you. It's the amount of given isotope of an element that exists in nature, and it's expressed as a percentage. So for example, let's go back to our carbon-12 example. And let's say, I'm just going to say C12. That means carbon atoms that weigh 12. Let's say that these represent 91% of the carbon population. Then you might have C13, a carbon that weighs 13. That might represent, let's say, 6% of the population. That's going to leave us with 3% of the population for carbon-14. So those aren't real numbers, that's just an example, but it goes to show you the idea of the weighting. Why is this important? Is because we want to know how many of each we have, right? You don't want to find the average of just doing 12 plus 13 plus 14, because that's not a true average, right? That would tell you that on average carbon weighs 13. We know that's not true. On average, we know carbon weighs 12.01. So that suggests that there's way more carbon-12s than anything else, so that isotopic abundance is actually really important. So we're actually going to be using that isotopic abundance to go ahead and calculate average atomic mass. So this is where we're going to get into the math. So I'm going to shut this video down in just a second so I can write. So there's actually two different ways to do this. I'm going to show you an easy way and a more challenging way. Why would I show you both? Because the easy way takes a little bit more time. It's easier to understand, but you're punching more values into your calculator. The more challenging way allows you to punch things into your calculator just once. So if you can actually get good at the challenging way, it's actually going to save you a lot of time. It actually has less rounding, and it's actually going to be more accurate in the long run. So I'm going to show you both strategies, strategy A, strategy B. You're going to be doing an activity after this, a lab activity. You pick whatever strategy is going to work for you. So let's take a look first at what we're given. What we've been given in this case is we've been told the isotopes that we're dealing with. So we've got copper 63 and we've got copper 65. All this 63 means is that copper that has a mass of 63, and all this 65 means is copper has a mass of 65. So it's just a way of telling us the number. We know they're isotopes because we are both dealing with copper. It's also told you the mass. So rather than just saying 63, 65, it's a little bit more specific. Copper 63 has a mass of 62.93, and copper 65 has a mass of 64.93. It's also told you the abundance, so the percentage in the population. Notice those two numbers do add up to 100%. So there's actually only two isotopes for carbon, and they're going to represent 69.2 and 30.8% of the population, respectively. So I'm going to start by showing you the long way first. I'm going to shut this video down so that way I can write not on an angle. Hope you can still hear me. All right, so let's take a look at strategy A. So strategy A is actually going to break this into two parts. So it's actually going to break it into the contribution for copper 63 and the contribution for copper 65. So essentially, the first thing that we have to do is we have to take the mass and we're going to multiply the mass by the percent abundance. Now, just a word of warning, I'm sure you've done this before. I'm sure you've figured out a percentage on your calculator before, but remember that when you're looking at something in terms of percentage, it's 69.2 of 100. So in order to actually turn this into a real percentage, we actually have to go ahead and we have to divide each of these numbers by 100. So when we're talking about the actual percent abundance, we're going to be using the numbers 0.692 and 0.308, right? I'm sure you've all decided what percentage you got on a test by going through, dividing the value by the total, and then multiplying by 100 to give you the percent. So that means we actually have all the information that we need. It's listed for us. We know the mass of copper 63. The mass of copper 63 is 62.93. And we know the percent abundance. The percent abundance is 0.692. All we need to do is plug this into our calculator. And when we plug this into our calculator, it's going to spit out 43.5476. And we always want to use units in chemistry. So remember, units for mass in this case is going to be just U, or you can use the longer AMU. Now, we do want to keep the correct number of significant digits. To keep the correct number of significant digits, we want to round by how many decimals we were given. Well, we were given 2 decimals here. We were given 1 decimal here. We always want to go with the lowest number, so we want to round this to 1. So we would actually round this answer to 43.5U. We want to do the same then for copper 65. So for copper 65, we're going to again take the mass and we're going to multiply it by the abundance. So my mass in this case is, I'm going to shrink down just a little more so you can still see the screen there. My mass is 64.93 and my abundance is 0.308. I'm going to go ahead and I'm going to punch that into my calculator. And when I punch that into my calculator, I should get 19.9984U. Remember, we always need that unit. So again, I do want to keep the correct number of decimals. I want to round to 1. If I round to 1, we're going to see that we're actually going to go up a whole number. So we're actually going to have to round 19.998 to 20.0. I'm going to keep that 0.0 there just to show that I do indeed have that decimal, the correct number of significant digits, and I'm going to put that U. So that's strategy A. Strategy A is looking at the actual individual components. And then, of course, to actually figure out the mass of the individual components, we would have to go ahead and we would have to add these together. So we have to take the contribution from A. So we have to take the mass of A, and we're going to add to it, sorry, I didn't mean to say A. What am I saying? We're going to take the mass of copper 63, and we're going to add to it the mass of copper 65. We want to take those two contributions and add them together. So I'm going to take 43.5 U, and I'm going to add to it 20 U, and total, you're going to find that we're going to get 63.5 U. So overall, our contribution for copper from each of them, our overall average atomic mass was said to be 63.5 U. We have to make sure we have that unit in there. Now, strategy B is going to be almost the exact same thing. It's going to be the exact same calculation, but rather than having to hit enter on your calculator one time here, and then one time here, we're actually going to go ahead and we're going to do this in one line. So to do this in one line, we're going to take the, we're going to take the mass of copper 63, and we're going to add to it the mass of copper 65. Now remember, the mass is not just the mass, it also takes into consideration the isotopic abundance. So I'm going to want to go ahead and take the mass of 63 times the percent abundance of 63, and I'm going to want to add to it the mass of 65 times the percent abundance of 65. Now notice I am using brackets here. That's to get the correct order of operations. So you want to make sure that you do the multiplication in the brackets before you actually add them together in your calculator. If you don't do the numbers, what's going to happen is these two values are going to multiply correctly, but then you're going to incorrectly add this value and then multiply over here. So you want to make sure that you are using the brackets in your calculator in order to get the correct answer. Now we want to go ahead and fill in what we know. Well, we know exactly what the mass of copper 63 is. It's 62.93 U, and we're going to times it by the abundance, which is 0.692. Brackets around it. We know what the mass of 65 is. It's 64.93. Wrote that backwards, didn't I? Almost gotcha. 93, not 39 U. And we're going to multiply that by our abundance, 308. And then I can actually punch this into my calculator in one line, and it's going to give me the total value of 63.5 U. So you can see that these answers are actually the exact same. All that this does is we don't have to worry about rounding, and we don't have to type as many things into our calculator. Now, I did give you some homework to practice as well too. Homework answers are posted. You're going to find that chemistry is actually a lot of math. I'm sorry, I hope someone told you that before. So math is all about practice makes perfect. So I definitely recommend trying these homework questions. Double check your answers, and then once you get the correct answers, you are ready to move along to our next activity, which is going to be a lab calculating the isotopes of pennies. Great job, and we'll see you in our next video, and we'll talk about some more chemistry then. We're going to talk about periodic trends. We'll see you later. Bye.